Thanks, Aria, for the introduction. Obviously, really appreciate the opportunity to talk to today. And obviously, a big thank you to everyone who joined in, took times out of their schedule. Hopefully, it proves worthwhile for you all. Just give me 1 second. I'll pull up my slides here. Okay, so today I'm going to be talking about preventing thermal runaway propagation in lithium-ion battery packs using Beam's patented phase change composite material. I'll provide a brief introduction into Beam Global as a company and the PCC technology. I'll then provide a quick introduction, occurrences, results of those occurrences, and root causes of thermal runaway propagation. And then the focus of the discussion will be around preventing those occurrences with the core technology of Beam being the PCC. I'll then tie that into key characteristic of the PCC in preventing that thermal runaway propagation, being thermal conductivity, and how we use the Trident C-Therm system, particularly the MTPS sensor, to quantify that thermal conductivity. Beam Global is a San Diego, Chicago-based technology innovation company. We provide complete solutions in fields of electric vehicle charging, as well as energy storage, energy security, and outdoor media. Here's a brief overview of the various products that we provide in various stages of development, as well as manufacturing and selling as well. If you joined early on, you would have seen our CEO Desmond provide a really good introduction into the EV ARC system, which you see on the left, which is a off-grid, solar power, rapidly deployable, portable car charging system. And we also have similar systems, again, in various stages of development for commercial fleets like busing applications, as well as drones. We're also looking at adding cloud networks and telematics to those kinds of systems as well. We also are looking at developing similar concepts for car charging in light poles along the street. And obviously, where sort of I come into the conversation through the acquisition of AllCell in March by Beam Global is with the Beam AllCell product portfolio, being the energy storage solutions. So the Beam AllCell sort of product portfolio looks at highly flexible, scalable battery solutions with the patented PCC thermal management technology. Our battery packs are optimized for unique applications, including drones, aviation, maritime, recreational products. Basically, this, as a broad view, is a host of micromobility and LEV products. Ideally, the PCCs and battery packs that we provide are suited to high power, high energy density, with safety as a key concept in the application. So diving into the phase change composite, or PCC technology, it's a composite material made up of compressed expanded graphite and wax, where the graphite is used to rapidly distribute the heat generated from cells during discharge and charge, and that's to enable uniform battery pack temperatures. Battery pack is a weakling sport, meaning that if you have hot spots in your battery pack, those temperatures cause rapid battery aging around that specific hotspot in those cells. And obviously this draws down the life of your battery pack. And so distributing the heat, as well as managing maximum temperature, which we do through the heat absorption of the phase change. So as the battery pack temperature heats up, the wax goes from a solid to liquid transition, and that absorbs an enormous amount of heat compared to specific heat absorption products like metallic materials. And that allows us to cap battery pack temperature, and obviously simultaneously distributing the heat uniformly as well. So you have you have low pack temperatures, but also uniform pack temperatures. So before diving into the thermal runaway and safety aspects, I do want to cover a couple sort of non-abuse or nominal condition benefits of the PCC technology and the battery solutions that we provide with these technologies. So here we look at a battery pack that's situated in the trunk of a car in Phoenix during the summertime, and you can see that the peak temperature of that day exceeds 65 degrees Celsius. And we compare the battery peak temperatures with and without PCC, and we see there's a large differential there in maximum temperature. Obviously, that's through the heat absorption in PCC. We also look at a cycle life improvement of the PCC for a specific two-wheeler application where you'll have high power loads like during regeneration. You'll also have high energy density applications, so you are really pushing these cells throughout its full depth of discharge and full discharge charge voltage profile. Excuse me. So the legend dropped out here, but the PCC battery pack in red was able to achieve greater than 100% improvement in cycle life compared to the non-PCC battery pack. And that's at obviously greater than 80% at the beginning of life capacity. The final case study we'll take a quick look at is for a drone application where you'll have constant high power discharge. And so what you can see here, as you start to elevate pack temperature through that high power discharge, the wax starts to melt, and you obviously maintain a uniform temperature. And so what you actually get is longer run time. So the drone doesn't have to prematurely land to cool down. You can actually keep the drone or other high power requirement applications running for longer below maximum temperatures to prevent any safety issues. One interesting benefit with this capability is that there's lots of applications that are sort of between a power versus energy cell, and a lot of manufacturers decide to move to the power cell so that they don't have, due to lower impedance, obviously you don't have as many thermal management issues when discharging at high power. But with the PCC, with its rapid heat distribution and absorption, we can actually transition those products and those applications into an energy cell. And so obviously that provides greater overall energy in the pack. But another significant benefit is reducing cost, since energy cells are much more cost competitive and are produced at much larger volumes than power cells. So to sum up those benefits, we were able with the PCC technology to protect battery packs against hot environments, distribute and manage heat to improve cycle life, enable use of high energy cells at high power operation. And the last one, which we'll get into now, is obviously preventing thermal runaway propagation, which is the focus of the discussion today. So thermal runaway is the uncontrolled excessive heating of a cell caused by abuse conditions to the cell, whether that be overcharging, external overheating. It can also be from mechanical damage such as crush or nail penetration, as well as any external short circuit damage to the cell. It can also occur without these occurring due to manufacturer defaults in the cell. So if a separator is folded or something like that, like what has happened recently in the news with LG and GM, and that can naturally lead to internal short circuits during various conditions. The result of those occurrences is you start to have reactions inside the cell between different active materials such as electrolyte and cathode or anode materials. That's exothermic reaction, so the cell heats up to a point where if the heat released from the cell doesn't match that, you obviously get continual heating to a point where the separator melts. And that separator is obviously varying chemistry, but 150 to 170 degrees is sort of that ballpark temperature where the separator melts. At that point, you have internal short circuiting throughout the cell and really massive current dumping throughout the cell, obviously excessive heating. And so you can see on the curve on the right here is basically very slow overheating the cell in an accelerating rate calorimeter, which we use to examine those thermal runaway threshold temperatures. And you'll see that the cell heats up to a point where that separator melts, and you just get a very rapid, over a couple seconds, sort of energy dumping throughout that cell. And as you see in the picture here, it's quite a violent reaction where the electrolyte will be pressurized, it will release through a safety vent in the cell and combust upon exposure to air. I think one key message that I think part of this is that the energy that releases from the cell during a thermal runaway is 60 to 70% caused by that combustion of the electrolyte. What is thermal runaway propagation? Well, the propagation aspect is when that failure spreads to neighboring cells like a domino effect. And that's caused by obviously the heat coming from that failing cell spreading and overheating surrounding cells. So heat and the thermal distribution is a major problem, and obviously a key topic of today's discussion. But also want to make mention that you can also get electrical shorting problems that occur through battery packs during a thermal runaway event, and that can also lead to internal heating or current dumping from neighboring cells as they're experiencing external short circuiting, which is obviously a root cause here on causing thermal runaway in those cells as well. So you both need to deal with the thermal problems as well as dealing with the electrical problems as well. So I just want to point out, obviously, this has been a major problem in the field. There's sort of lots of back and forth about, is it a major problem and things like that. If you look at aspects around comparing to gasoline vehicles, and that electric battery fires in vehicles have been a much smaller percentage compared to gasoline fires, I think that's one thing. But really, I think the key message here is that the electrification industry is booming, and we need to make sure that we're not just serving that need with products that meet current safety standards, but we're continually pushing the envelope in the safety of our products that we're pushing out. And so I think one of the major problems is battery manufacturers sort of producing products that don't meet minimum safety standards. And I think we're really starting to get some momentum to move towards standards that really look at strong safety thresholds to really start to minimize these problems that happen in the field. So before jumping into the PCC advantages in thermal runaway propagation, I do want to cover some thermal runaway misconceptions in the community. Obviously, there's been a lot of discussion around the safety comparison between LFP and high nickel content batteries, and lots of statements around the fact that LFP is safe or safer. Obviously, LFP is a different cathode chemistry, and so you get different characteristics during a thermal runaway, like different threshold temperatures for that thermal runaway to occur, different energy outputs from that LFP. I think the key factor in by stating the 60 to 70% of the energy output is because the electrolyte combustion, well, the electrolytes are somewhat similar, and so you do still have during LFP thermal runaway a massive output of energy. It may be high to get to that threshold, but there's no doubt that LFP batteries have had major problems in the field in terms of thermal runaway and thermal runaway propagation. A good example is the recent EV bus fire in China that employed BYD LFP cells. Another statement is about solid state. So the removing of those electrolytes and transition to lithium metal is being safer or safe as well. Again, different chemistries, so you can have vastly different mechanisms and thresholds behind what happens with thermal runaway, but thermal runaway and the propagation of that thermal runaway can still occur and has occurred in the field. And a recent example is the Paris Ballore electric bus fire. So this had not only the removal of the liquid aprotic volatile electrolytes, but it also had and sort of implementation of a solid state or semi-solid state polymer electrolyte, but it all with the lithium anode, but it actually also had LFP cathode as well. And thermal runaway was quite catastrophic in that event. The other misconception I want to cover is sort of when looking at battery pack solutions or claims of preventing thermal runaway, you just really want to make sure that this is it's sort of in-use application analysis. And why is that? Well, it's actually quite it's a much easier requirement to pass thermal runaway propagation testing, so to prevent the propagation from a single cell failure in open environments. So if you look at testing that we've done internally to prove this out, we took 21700 811 NMC cells with very minimum 2 millimeter spacing. We had no thermal management, so no PCC or other thermal management. They were just held 2 millimeters apart using PVC holders with no spacing with no sort of protective materials in between. And you can see that on the graph on the left there that there's no propagation, and actually the neighboring cell temperatures only reached a maximum of about 80 degrees Celsius. But as soon as you transition that identical pack into a case, right, and so now you're sort of in-use application inside a battery pack case that would exist, the propagation was very rapid and very catastrophic and actually continued throughout the entire pack. And you can see images of that on the slide. So now moving into sort of the benefits of PCC in solving this issue. I think this is just an introductory slide just to showcase how propagation looks from a data perspective. So we ran both simulations and experiments, top and bottom, for a battery pack that was a 4S 10S4P, sorry, with about 1.5 millimeter spacing, so quite tight spacing. These were MG1 cells, so sort of older model cells. I think about 2.9 amp hours, but high energy at the time. You can see that on the left where we did not have PCC between the cells and they were just held in place by PVC, you have sort of the initial spike in temperature from that failing cell on the far left at time 0. And then within 10 seconds, you have the first initial propagation of the neighboring cell. And it's just a domino effect beyond that throughout the entire pack. And so that gives a good sort of overview of how the propagation occurs and how it looks from a data perspective. You can see that the temperatures there exceeding 600 degrees in the initial, and then cascading failures in this particular pack were still close to 400 degrees Celsius. Obviously, we take the same pack and replace those PVC holders with our PCC technology, and you can see that the initial failure that we induced with the nail penetration still occurred, but neighboring cell temperatures remain below the critical threshold for these cells, about 150 or 170 degrees. And because of that, there was no propagation that occurred. So one case study that I want to cover is one that we did in conjunction with NASA, looking at how thermal conductivity and how latent heat is important for, and the combination of those is important when preventing thermal runaway propagation in these lightweight, high energy density battery packs. So again, we're looking at the same battery pack as the previous slide. So again, the 4S10P with the older model energy cell, but still NMC with high nickel content. We compared a pack with the PVC spaces only, see on the top left there. We also took a pack with compressed graphite. So we took similar density that we use in our PCC, but didn't add the wax material into the matrix, and just ran a test on the graphite. We also did the reverse of that and just had wax surrounding the cells without any graphite to aid in the thermal conductivity. So just had the latent heat with very low thermal conductivity. And then finally, we ran similar testing on the PCC. So the table there obviously shows the differences in key attributes, being the conductivity and the latent heat. So minimal latent heat for the air and the graphite. Obviously, for the wax and the PCC, you do have that injection of latent heat. For the graphite only, you obviously have the highest latent heat, the second highest latent heat. And then you maintain and actually grow that latent heat with the addition of wax into that for the PCC. Wax having low latent heat as well as like the air between the cells is what we use for the thermal conductivity measurement in the air test. So the conclusions at the bottom of the slide, and we'll get to the data next, but PCC prevented any propagation. The other tests, propagation occurred. So I've just taken snips of the data here for the air test just to show you what the air test was like. I haven't included the graphite or wax test, but this work is published, so feel free to reach out, and I'm happy to drop a link to that publication. So what you can see with the PCC test, again, to the couple slides ago, is that you get that initial spike in temperature with the induced failure in the trigger cell, and then the neighboring temperatures spike to around about 100, 110, but remain very close to that threshold. And we're continually doing development to push the PCC and optimize the PCC closer and closer cell spacing so that we still maintain that threshold temperature. You know, I mentioned threshold of that thermal runaway being about 150, 170, but we like to provide a buffer, especially if you get a failure at sort of high ambient temperatures and things like that. You want to make sure that there is a buffer there. Compared to the air test, obviously you get the initial spike in temperature due to the induced failure in the purple curve at around about 50 seconds. And then within seconds, you get propagation of neighboring cells, and propagation continues throughout the whole pack over several minutes. So one interesting development in the community is the 9540A certification. So 9540, which is the overarching safety standard, is a general safety standard for energy storage systems, and it's a system level. So if you know, for example, the EV ARC system contains not only battery pack but inverters and other components that we look at certifying the ARC. And what this therefore pushes is safety requirements on the battery pack, which is usually the 1973, which includes the nail penetration and sort of a request or a requirement rather to prevent propagation in the 1973 standard, and obviously prevent any sort of toxic vapors and explosions from escaping the battery pack. But the 9540A is a developing standard that is required when you have sort of residential systems or systems that are non-residential but sort of remain in close contact to surrounding structures, as well as those that are have you know, larger energy. I think that the threshold is around about 50 kilowatt hours at the moment, but I think the community is continually pushing those thresholds, and they're always developing and changing. So with sort of pushing the boundaries in passing these certifications and doing that with higher and higher energy densities and smaller battery packs, we constantly are looking at developing new materials in conjunction with the PCC to surpass these certifications. So obviously one of the big new requirements with this 9540A is to not only prevent multiple propagations, you actually have to be able to induce propagation, have a natural propagation occur beyond that. And then it's okay to have propagation beyond that, but you can't have any visible fire or explosion or toxic vapors outside of the battery pack. So this is more of a containment certification in certain sort of residential or large scale energy storage systems. And so obviously the PCC can be designed so that you can limit the need to have containment, so reduce the propagation that occurs in the battery pack, but you can't use PCC to prevent the fire and explosion that naturally occurs due to the release of those volatile gases. So what we've developed and patented, and we're continually developing for commercial sale, is our hydrogel, which we'll incorporate into our battery packs. This is a composite material of super absorbent polymers and moisture that goes through a phase change when obviously exceeding the vaporization point of water. And so this does twofold. One, it can absorb a huge amount of energy release from a failing cell, which really helps in smaller battery packs where you have a lot less thermal mass to absorb the heat throughout the battery pack. So it really helps in small battery packs where you really want to condense the spacing between cells, so power till applications, etc. But also the vaporization of the water reduces, quenches flames, and it also removes the flammable materials outside of their explosion limits. So it has multiple benefits to adding to the ability to pass these certifications. And it's something we're really excited about and continually focused on developing. So just want to tie in sort of the thermal conductivity aspect to PCC. So the thermal conductivity that we optimize for PCC helps in thermal management, as I've said previously, to provide uniform temperatures and extend cycle life. It also is essential, as I showed through the case study with NASA, to prevent the propagation. And so our philosophy behind that is, rather than trying to isolate that cell, we actually try and very quickly distribute the cells and make use of the surrounding thermal mass. There's obviously others in the community that isolate the cell through different ceramics, etc. But obviously the benefit with the PCC compared to that is that we can also add benefit during non-abusive conditions as we provide the thermal management by heat distribution and heat absorption. And finally, the thermal conductivity for us can actually be a good means of checking for structural integrity as well. So correlated to density, and obviously Aria touched on how different continuity in materials can change the thermal conductivity. Obviously, for that also impacts the structural integrity as well. So we can make good correlations there in our testing. We've used the thermal conductivity technologies from the ground up design of our PCC, optimized around density, optimized around the graphite morphology and chemistry. We can change thermal conductivity aspects as well as various other aspects that are important for PCC optimization. The same can be said for wax content and chemistry of the wax as well. And then finally, manufacturing process. There's lots of optimization around the manufacturing of PCC. Obviously, it's our bread and butter, and thermal conductivity is one gauge of that optimization. We have used the MTPS Trident system over the past 12 months. We selected that after a quite extensive comparison to our existing technology, which was laser flash analysis. And sort of we decided on the Trident system because it was much more cost competitive. It had extreme simple testing and sample preparation compared to laser flash. One thing that we enjoy is that it's portable, so we have obviously multiple sites. We can transition this between R&D lab or the manufacturing plant, and then the quality control areas as well. Since this is such a fast and rapidly deployable system, we can actually spot check for quality control of our PCC as well, which has been really useful. And then Aria and Adam touched on this previously, but it is really accurate for anisotropic materials and composite materials, which is obviously our PCC. And so we've really enjoyed it for those reasons. There's a picture there of our materials engineer, Hugh, using the system in our lab, and he definitely agrees with the conclusions about the Trident over the LFA. So finally, I just want to make sort of the summary statement that PCC is an exceptional tool in the preventing of thermal runaway propagation in our battery pack solutions. But preventing thermal runaway propagation is not a one-stop shop. It needs to be done with a holistic viewpoint, a holistic design approach. And the reasons for that is there's multiple mechanisms that can cause propagation. Once that initial cell fails, there's thermal, which can be split up into multiple between sidewall rupture directly facing onto other cells, to the release of the hot flames through the vent, and obviously the cell-to-cell conduction through any interstitial materials. But also there's an array of electrical short-circuiting issues that can result and have multiple pathways and multiple sources. And so that's a key aspect that we've spent a lot of time on investigating and optimizing over the last several years. And we have peer-reviewed papers that we've recently published on that I dropped a link to, basically looking how connections versus no connections between cells can drastically change the results of propagation. And so it's definitely something that you need to optimize in your battery pack to protect both against the thermal and the electrical shorting problems. So finally, just want to acknowledge, obviously, the huge amount of support and efforts by the full Beam team, as well as our partners at Illinois Tech and University of Illinois Chicago, that have combined to not only develop the PC and optimize the PC and the holistic sort of safety design approach of our battery packs, but also help with this presentation and portray this information to you guys. So thank you to all those listed here.